Hello everyone, my name is Dre Gibson. I'm here on this lovely day to help you go through the problem of the closed capillary tube with equal volumes of ideal gases A and B separated by a divider, where it is then allowed to mix to a uniform composition. And this is all done under constant pressure and temperature. So one thing that's important to note is if we look at the capillary and we choose a specific volume, so this is the volume here, and we take the total molar flux coming in of that volume and the total molar flux coming out of that volume, we know that these have to be equal. Why is that? That's because of the ideal gas law, and that is the number of moles over the volume, which is equal to the pressure times the ideal gas constant times the temperature. And we know since the pressure and the temperature are constant throughout, that the number of moles throughout this volume also has to be constant throughout. So therefore we know that the total molar flux is constant throughout the capillary. So that means that the total molar flux, which is equal to the molar flux of A times the molar flux of B, is constant. But what is this value? This is a closed capillary tube, so we actually know that at this point and this point, since it's a closed end, that the total molar flux is equal to 0. And since we know that it is constant throughout, we know that throughout the entire tube, the total molar flux is equal to 0 everywhere and always. And why is this important? Well, this is important because if you look, we know the total molar flux is equal to the total molar concentration of the gas times the molar average velocity. So therefore, if this is equal to 0, we know that the concentration of the gas can't be 0. So that means that the total, or the molar average velocity has to equal 0. This is important because it allows us to relate the molar diffusive flux and the mass diffusive flux. I think it's important to first go and describe what the formulas are for the molar diffusive flux and the mass diffusive flux. So the molar diffusive flux is equal to the concentration of A times the velocity of A minus the molar average velocity. And the mass diffusive flux is equal to the mass concentration of A, or density, times the velocity of A minus the mass average velocity. And so, like we derived before, we know that the molar average velocity is equal to 0 because the molar flux throughout the capillary is equal to 0. So therefore, we know that this term goes to 0. And we can rewrite this as the molar diffusive flux is equal to the concentration of A times the velocity of A. And more importantly, we want to write this as the velocity of A is equal to the molar diffusive flux of A over the concentration of A. So there, we can then plug this in to the mass diffusion flux formula. And that will allow us to relate these two formulas. So therefore, the mass diffusive flux is equal to the mass concentration of A times the molar diffusive flux of A over the molar concentration of A minus the mass average velocity. And at this point, I think it's important to look at what the mass average velocity is. The mass average velocity is equal to the mass concentration of A times the velocity of A plus the mass concentration of B times the velocity of B over the mass concentration of the combination of the two gases. Since this is a binary system, we're just looking at the mass velocities of 2, so therefore it's just adding a sum of the 2. And therefore we know that if we plug back in the velocity of A into this velocity of A, we can get that the mass average velocity is equal to the mass concentration times the molar flux of A over the molar concentration of A plus the mass concentration of B times the molar flux of B over the concentration of B. And this is just the same relationship with the ideal gas of B rather than the ideal gas of A. It's interchangeable. And we take this and divide by the total mass concentration of the gas mixture. And so what we would do here is we know that if you have the mass concentration over the molar concentration, this is the same thing as, say, mass over volume over moles over volume. And that's your mass concentration over your molar concentration. And we know that since the volume is constant, that the volumes are going to cancel out. And so therefore you have mass over moles, which is equal to your molecular weight. So therefore you have your molecular weight of A. So we can rewrite the mass average velocity as your molecular weight of A times your molar diffusive flux of A plus your molecular weight of B times your molar diffusive flux of B, all over the total mass concentration. So now we're going to plug what we just found here and also our knowledge of the molecular weight being the mass concentration over the molar concentration and rewrite this formula below. So therefore we have the mass average velocity is equal to, now we have the mass concentration over the molar concentration, so we can rewrite that as molecular weight of A times the molar diffusive flux of A minus the mass concentration of A times, in this case it's going to be the mass velocity, but we're going to rewrite it as this derived equation here and write it as molecular weight of A times the molar diffusive flux of A plus the molecular weight of B times the molar diffusive flux of B over the total concentration of the gas. So this is a little bit easier to work with. We have some terms that we can kind of combine and use some other relationships to get a relationship between the mass diffusive flux and the molar diffusive flux. So next important concept to talk about is the sum of the molar diffusive fluxes are equal to 0. And why is this? This is because the molar diffusive flux of A is going to be equal to, in this case since it's a binary mixture, the opposite direction of the molar diffusive flux of B. And this is because as the gas is diffusing into the other side is also diffusing into the first side. So therefore they're equal to 0 because they're basically combating each other. So therefore we have the molar diffusive flux of A is equal to the negative molar diffusive flux of B. So then we can use this to rewrite our mass diffusive flux formula, and therefore we're going to rewrite that as the molecular weight of A. Well, actually, for simplicity, let's pull out the molar diffusive flux of A. And that would then be multiplied by the molecular weight of A minus the mass concentration of A times the molar diffusive flux, now I pulled that out, times the molecular weight of A minus the molecular weight of B over the total mass concentration. Now we can simplify this a little bit further because we know that the mass concentration of A over the total mass concentration is the mass fraction. So therefore we have the mass fraction of A is equal to the mass concentration of A divided by the mass concentration of the gas. So therefore we can plug in the mass fraction in to simplify this equation further. And therefore we have the mass diffusive flux of A is equal to the molar diffusive flux of A times the molecular weight of A minus the mass fraction here times the molecular weight of A minus the molecular weight of B. And this gives you a nice formula that you can then use to relate the mass diffusive flux to the molar diffusive flux. I realized that the formula is a little cut off here at the bottom. But this is an important relationship because now we have the mass diffusive flux is equal to the molar diffusive flux times the molecular weight of A minus the mass fraction of A times the molecular weight of A minus the molecular weight of B. And this is important because if we know one of the diffusive fluxes and we know the mass fraction, we can essentially solve for the other diffusive flux. Because we know the molecular weights are always going to be known values because they are going to be pulled from the periodic table or given molecular weights. So therefore, given those three, we can solve for the other, and therefore we have related the mass diffusion flux and the molar diffusion flux. Thank you.